Last time we started a description of angular momentum. We established certain relations. Let me just summarize the basic stuff that we derived last time. Remember that we have these commutation relations. Okay, they just go cyclically. Okay, Ly. So once we have these, we show that we can look at the commutation relations of the L squared with any one of these, okay, Lz turns out to be 0. In fact, obviously, this is going to turn out to be 0 for any direction in space. Okay, so I get a set of relations which look like that. So since L squared and any one of these directions commute, we choose one of these things. We cannot choose all of them because they do not commute among themselves. Okay, so we choose just one of them and we favor Lz. Okay, we say that let's find eigenstates of L squared and Lz. Okay, so they'll be simultaneous eigenstates of those two operators. Okay, that's possible because they commute. Okay, so okay, I'm destroying a computer here, but okay. In any case, I have a so I say that I have this eigenstate with two different eigenvalues depending on what I operate on it with it. So if I operate on it with L squared, I get h bar squared. Remember, units of L squared is the same as units of h bar squared, so that I factor that out to get a unitless number lambda. So that's my eigenvalue, lambda m. And similarly, Lz, lambda m, is going to be h bar times m, lambda m. So I know that such eigenvectors must exist because L squared and Lz commute. Okay? And now let's, okay, the next thing that we did was we used these nice operators. We define them as L plus or minus. Okay, so depending on whether you get the plus or minus, you get Lx plus or minus I Ly. Okay, so that's my definition of L plus or minus. And what we demonstrated was that if now I have, if I operate on this eigenstate, lambda m, with an L plus, I get something which is still an eigenstate of L squared with exactly the same eigenvalue. So that means whatever this is proportional to, okay, we have to find the constant of proportionality today, but it has the same lambda, but the m eigenvalue is 1 higher, so that I get h bar m plus 1 as the eigenvalue. So the Lz eigenvalue is h bar larger. And I left this as an exercise to you. I am sure all of you did it, right? L minus lambda m is lambda m minus 1. Okay, so it reduces the Lz eigenvalue by an amount 1 h bar. Okay, so we have this energy structure. So Griffiths makes a picture of this very eloquently as a cat climbing a ladder, both on the cover of the textbook and also inside. But what I have is a bunch of eigenstates, which are, okay, so if I just happen to find one of them, it corresponds to lambda m. And by operating on it by L plus, I obtain lambda m plus 1, okay, lambda m plus 2. So these are the LZ eigenvalues, right? They are going to be m h bar here, okay, m plus 1 h bar there, and so on. So this is going to be m minus 1 h bar, etc. So I'm going to get a set of eigenstates which look like that, okay? So that will be the structure. So all of these things have the same lambdas, you see? When I operate on it with L plus or L minus, I do not change the lambda, okay? So the total angular momentum eigenvalues are the same, but the LZ eigenvalues increase or decrease by 1. So this whole thing has some total angular momentum, and we argued that there must be some, okay, lambda m max here, and there must be some lambda m minimum here. Why? Because the z component of the angular momentum cannot increase indefinitely because I have a total angular momentum. Okay, so it is restricted by some number. And then also if I have this m minimum, okay, that is going to be also the limit for the most negative value for the angular momentum. Okay, so these things I gave a name, so m max I'm going to call L, m min, just due to symmetry, it has to be minus L, okay? So there's no difference between plus Z and minus Z direction. If I have a certain maximum in the plus Z direction, I must have a similar magnitude, okay, limitation in the minus Z direction. Okay, so that's the structure that we have. All right, so let's now try to find out what this maximum and minimum m's are. How can I find it? Well, just remember our methodology from the harmonic oscillator. If I try to raise this by 1 or lower that by 1, I should get 0. Okay, so if I try to, okay, so L minus takes me down, but L minus here should take me down to 0. And similarly, L plus, okay, should take me to 0 over here again. All right, any questions? This is more or less where we were last time. Okay, so let's just look at that. I have L plus operating on lambda m max, okay, has to be 0. So let me find the magnitude of this vector. How do I find the magnitude of any vector? I multiply it, okay, I find the inner product of it with its adjoint, right? So what is the adjoint of this? Well, okay, it's 0, very nice, but how do we calculate the adjoint if you want to calculate it in detail? So the adjoint of this piece is lambda m max. Okay, so the ket turns into a bra. What does L plus turn into? L minus. Okay, it turns into its adjoint. So in place of I have to put the minus I. So that's the adjoint of this. And then I have L plus, right, lambda m max. And this has to be 0, right? This size has to be 0. So now I have this L minus L plus. Let's work that out. So the L minus L plus is going to be Lx minus I Ly, Ly, no, oops, sorry, Ly Lx plus I Ly. Okay? So what does that give me? Well, it gives me an Lx squared, so the direct terms are easy, plus Ly squared. Okay? And then I have the cross terms. So I have minus I Ly Lx plus I Lx Ly. So it is commutator of Ly with Lx. Okay, so it comes in as minus Ly Lx, but plus I, okay, Lx Ly. So this thing here is Ly Lx, okay, wrong order. So it comes in as minus I h bar Lz. This Lx squared plus Ly squared, I can write as the total angular momentum squared, which is Lx squared plus Ly squared plus Lz squared, but Lz squared is missing, so minus Lz squared. Okay, so this is a very nice and useful relation. Let me just write it one more time. Ly, L minus, L plus is equal to L squared minus Lz squared minus, okay, I times I is minus 1, so minus h bar Lz. So what's nice about this is that the eigenstates that I have here are eigenstates of these operators, L squared and Lz, so it makes my calculation possible. So in fact, so important, I'll put this on this board also. Okay, so I'm going to put here L minus L plus is equal to L squared minus Lz squared minus h bar Lz. Okay? So let's now just put that into our equation here. All right, so I get lambda m max L squared minus Lz squared minus h bar Lz lambda, okay, lambda m max. And this is supposed to be 0. Okay, but now what are these quantities? I know what L squared times this is. Okay, it just gives me lambda times h bar squared. So I get lambda times h bar squared minus Lz squared. What's that? Yes, m max h bar squared, right? And minus h bar times one factor of that, so it's going to be h bar m max is equal to 0. Okay, the bra and the cat just are normalized to 1, so they disappear. So I just cancel the h bar squareds. And what do I get? Lambda equals m max squared plus m max. Okay, so I have been carrying out this m max just to emphasize that it's the maximum value of m, but that's something that I called L. Okay, so this lambda is equal to L times L plus 1. Okay, so this now enables me to determine what, for a certain value of L, the total angular momentum is, or conversely, if I know the total angular momentum, I can find out what the maximum value of the z component of L can be. Okay, so maximum value of m cannot be equal to, okay, whatever the total value of the angular momentum. It has to be less than that, right? Okay, so that's one result. Let's just verify that the other limit also holds. It should hold, but let's just, for the exercise, let me in fact continue it over here. Let's just look at the case when what happens when I try to lower this lowest eigenvalue by one step. Okay, so in that case, so the algebra is going to be quite parallel. I have L minus lambda, okay, m minimum this time has to be 0. And again, if I just look at the magnitude of this, it's going to be L minus lambda m minimum. Inner product with its adjoint, so it's going to be lambda m minimum. Okay. I have to use a different font. Okay, times L plus has to be equal to 0. But now I have L plus L minus, the opposite of what I had over there, L minus L plus, but I can again work it out very simply. L plus L minus is just Lx plus I Ly and Lx minus I Ly. So I'm going to do this somewhat quickly because we did it once, and I can do it somewhat faster the second time. So it's Lx squared plus Ly squared, this time plus, okay, I, commutator of Ly with Lx, okay? So Ly, Lx with a plus sign, Lx, Ly with a minus sign. So this is again equal to minus I h bar Lz. So the whole thing is equal to L squared minus Lz squared, okay? So Lx squared plus Ly squared is total L squared minus Lz squared. And then here now I get plus h bar Lz. Okay, so, well, just to be symmetric, let's also put down L plus L minus over here. L plus L minus is going to be L squared minus Lz squared, but plus h bar Lz, right? So, going back here, I have lambda m minimum, L plus L minus, which is L squared minus Lz squared plus h bar Lz, okay, and lambda m minimum equals 0. Again, I get h bar squared times lambda for L squared minus, okay, Lz squared, which is going to give me h bar times m minimum squared, okay, plus h bar times m, okay, another h bar, m minimum is equal to 0. So again, if I cancel the h bar squareds, I end up with lambda equal to m minimum squared minus m minimum. Okay, so again, if I just substitute minus L, okay, for, okay, that's my prediction. I said that if the highest maximum m is going to be plus L, the minimum L has to be minus L. So you see that I again get L squared plus L. Okay, so it is consistent. So now I'm going to change the notation just a little bit so that we conform with the proper convention. What I'm going to do is, okay, so let me just change definition of lambda m. In place of lambda m, I'm going to put Lm because L plus 1 is the maximum value that the total angular momentum can take. So it's okay, conventional to use that variable, that L quantity for the total angular momentum. So how does that modify everything? Well, I had L squared, now Lm. So L is an indicator of total angular momentum. So the total angular momentum is going to be h bar squared L plus 1 times Lm. Okay, so it's the same thing, except that this thing I used to call lambda. Now I'm going to call it, okay, L times L plus 1. And just rename the set vector and the bra vector, of course, so that they are labeled by the number L, which is the maximum value that m can take. So the z part, of course, doesn't change. So Lz, Lm is going to be h bar times m times Lm. Okay, so they are the same old eigenvectors, except that I am giving them a new name. Okay, instead of calling the index lambda, okay, which helped us all the way over here because, okay, writing the eigenvalue as proportional to lambda is much simpler, okay? But in terms of naming things, it just is the same thing. Okay, so what does that mean for the eigenvalue structure? So I have a structure in which I start from some plus m and go all the way to minus m. Okay? So I have something like this. Suppose I start with m equal to 2, then I have m equal to 1, m equal to 0, m equal to minus 1, and m equal to minus 2. Okay, so I have a set of angular momenta values corresponding to these. So what does that mean? This point, for example, corresponds to the measurement of Lz giving me 0. Here, measurement of Lz gives me 1 h bar. Here, measurement of Lz gives me 2 h bar, and so on. Okay, so this is minus h bar, Lz, I shouldn't really say equal to Lz is an operator. This arrow I mean to indicate a measurement. So those are the values that I can get out of a, this computer is going to have a very low half-life. If it goes like, okay, so in any case, so I have some structure like this, which corresponds to a maximum value of 2, okay, which means that these are all under the same L squared. So a measurement of L squared here is going to give me this maximum value 2 plus 2 plus 1, okay, L plus 1 times h bar squared, okay, so it's going to be 6 h bar squared. Okay, so let's look at that carefully. Okay, so suppose I make these measurements. So here is my atom which is coming in, it has some amount of angular momentum. And I'm going to measure its total angular momentum. Okay, so I'm going to measure its L squared. So what are the possibilities? Well, it's something which goes like L plus 1, and L plus 1 has to be, the L has to be, okay, the way I structured it here, we'll see an important exception, but at present, it's going to start with from a minus integer, okay, go to a plus integer, and it has this maximum m value, which can be 0 or 1 or 2 or whatever, okay? So the object that comes out flying here, okay, has one of those total angular momentum values. So what can they be? They can be 0 h bar squared, or it can be 1 times 1 plus 1 h bar squared, okay, so 2 h bar squared, or it can be 2 times 2 plus 1, so 6 h bar squared, okay, and so on, okay, 3 times 3 plus 1 h bar squared. So those are the possible values of the eigenvalue of L squared, okay? So it corresponds to L equal to 0, L equal to 1, L equal to 2, L equal to 3. So we, instead of labeling them in terms of these total angular momentum values, what we say that this measurement gave me L equal to 0, this measurement gave me L equal to 1, this measurement gave me L equal to 2, this is L equal to 3. Okay, so I label these states using L equal to 0, 1, 2, 3, 4, which is an easier way of labeling them instead of using the eigenvalue. Okay, so the eigenvalue itself changes as L plus 1 times h bar squared, but the index goes 0, 1, 2, 3, etc. So whatever value of L that comes out here, now I want to measure, okay, here I know now that my state is, okay, L equal to 1, but I don't know the z component of the angular momentum. So now I want to measure the z component, okay? So here I put an LZ, and what are the possible values for LZ?
0, 1, minus 1.
Yes, 0, 1, and minus 1 h bars. Okay, so here we again traditionally start with the largest one. So it's the m h bar, 1 h bar, which corresponds to m equals 1. Then 0, okay, this is m equal to 0, or minus h bar, which is m equal to minus 1. Okay, so those are the three possible values for L equal to 1.
Yes, but isn't for L equal to 1, mx equals to 1 plus 1 times 1 plus 1 equals 2. So why don't we have m equals 2?
No, we don't have m equal to 2 because the largest that I can have with L equal to 1 is L. Okay, so if L is equal to 1, m changes between minus L and plus L. Okay, so if you remember the structure of the eigenvalues here, you see the minimum one we said m equal to minus L. The largest one is plus L. Okay, so we are going to be, okay, constrained. We are between those two values. Okay, so if I make a measurement of total angular momentum 0, and I try to measure what LZ is, what are the possibilities? 0, right? Because this now the total angular momentum is 0. There is no way you can expect to get any component to be finite, right? So the only possibility here that you can get is, okay, m equal to 0. Okay, so just for fun, let's look at this. So I look at all these L equal to 3 stuff. So what are the possibilities?
3, 2, 1, 0, minus 1.
Okay. So you get the idea. So you get m equal to 3, right? M equal to 2, m equal to 0, m equal to minus 1, and m equal to minus 2. Okay, so a consequence of this is that you get all of these things, okay, all of these possibilities, starting with the plus L value. Okay, so this m equal to 3, the maximum one is equal to L, and the lowest one is equal to minus L. Okay, and here you see it's the L equal to 3 case. All right. Okay, so we have this eigenvalue structure for all of the eigenvalues. Any questions? One thing that's important is to notice that the z component of the angular momentum is quantized in units of h bar. Okay, 0 h bar, plus h bar, minus h bar, whatever, but we never have here in this structure 3.2 h bar, for example. Yes?
So in this scenario, we first make the measurement for L squared so that
Yeah.
we can have a prediction for Z component.
Yeah.
But what happens if we make first the Z component measurement?
Well, okay, so what will happen? Suppose I make a measurement of, say, Lz, and I get something. Okay, so here comes my atom. Now I measure Lz, and suppose I have all these possibilities. Now Lz can be anything, right? Because I don't know what L squared is. So Lz can be anything. Suppose I measure this, okay, z component of the angular momentum to be 3h bar. Okay. Now I want to measure what L squared is. Okay, so there will be a number of possibilities. So what will those possibilities be?
Anything greater than L equals 3.
Yes, okay, so there's no way I can get an L equal to 0 out of here, L squared equal to 0 out of here, right? Because if the total angular momentum is 0, I shouldn't have gotten an Lz equal to 3h bar. So the lowest L squared that I can have here is going to be L equal to 3. But it could be L equal to 4, it could be L equal to 5. In fact, there's no limit to this, okay? So it can be a state of the L equal to L16 state, right? So that we have to measure and find out which one it is. But it cannot be L equal to 2 or L equal to 1 or L equal to 0 because the z component is also already 3h bar squared, okay? Or 3h bar. Other questions? All right. So let's also solve this technical detail about what the proportionality constant is in this stuff. So let me just erase this. Okay. So the proportionality constants. So I have L plus operating on Lm. I know is going to give me another state, okay, which is going to have the same total angular momentum number, L, because it's not changing that. L plus commutes with L squared. So that's going to be L and m plus 1. So it goes up in m by 1. So what is this proportionality constant? Let's call it C plus. So if I want everything normalized, so if this is normalized, I want this L m plus 1 normalized also, so that I can just use it very nicely. You remember that in the harmonic oscillator we had these square root of n and square root of n minus 1 factors coming in with these a plus and a minus operators. So we are looking for the same sort of stuff here. Okay, so how do I determine this? Well, I find the magnitude of both sides. So I find the inner product of both of these objects, okay, with themselves. So we know how to do this. Just use the adjoint, Lm and L minus L plus Lm. On the right-hand side, the adjoint of C plus is C plus complex conjugate. So I still have the C plus. I'll take it out of the kit. L, or the inner product, m plus 1, L, m plus 1. But I just told you that this I want to be equal to 1, normalized, so that disappears. So this right-hand side is just magnitude of C plus magnitude squared. So now I'll have to determine what this L minus L plus is. We already did that once, but we did that for the case when the right-hand side was equal to 0, and this was equal to m max. Okay, so let's do it now for the general case. My equation for L minus L plus is over there. So this thing here in the middle is going to be L m L squared minus L z squared minus h bar L z L m. So that's going to be equal to, okay, just as we did earlier, h bar squared, right? Everything is proportional to h bar squared, so let me factor that out. Eigenvalues of L squared were L plus 1, okay, minus Lz squared, so that's m h, well, h bar I factored out already, so m squared, minus h bar m, okay, no h bars, sorry, maybe this is confusing. Let me just put the h bars in. Okay, so the first term is h bar squared L plus 1. The second term is minus h bar squared m squared minus h bar times h bar m, okay, is equal to C plus magnitude squared. Okay, so now we say, well, let's take C plus to be real and positive. So C plus is going to be equal to square root of, there's an h bar, this is the cursor of the h bars. I have h bar L plus 1 minus m plus 1. Okay, so again, an easy way to remember this is that you remember that when m reaches the maximum value, when m becomes equal to L, there's no other place to raise this object. So you get 0, right? So when L is equal to m, you are going to get 0 for the next object that you have. So you get this L plus 1 equal to that. Okay, so let's do the same thing for the L minus as well, for the lowering operator. Same sort of stuff. So again, I'm going to do this a little more quickly. So that means I'll probably make a mistake, so check my algebra. L minus Lm is going to be equal to C minus times L m minus 1. Now, again, if I just find the magnitude of this, it's going to be L plus L minus this time. Lm is equal to C minus complex conjugate times C minus. And then I have Lm minus 1, Lm minus 1. But the whole idea is, again, to get these things equal to 1. So I'm going to put 1 in there. And then this object here is exactly like that one. So it's going to be, okay, Lm, apart from a change in sign, so I have to be careful, L squared minus Lz squared plus h bar Lz. Lm, okay, which gives me h bar squared L plus 1 minus h bar squared, okay, m squared plus h bar squared m. So that is equal to now magnitude of C minus squared. Okay, so C minus then is equal to, assuming again it's real and positive and everything, just the square root of this. There will be 1 h bar, square root of L plus 1 is still there, minus, okay, you can check that this is equal to m plus 1. Okay, so the only difference between this and that is a sign change over here, okay, m plus 1. So you can again check very easily that if you are in state m equal to minus L, you cannot go any lower. Okay, so if I put in here minus L and minus L, okay, so what do I get?
So
Yes.
there is no sign sense.
Hmm?
Same.
Excuse me?
C plus and C minus are same.
Oh, I'm sorry. It should be minus here, right? M squared minus. Okay, so otherwise it doesn't work also, right? So minus L, so this is just going to be L plus 1 again. So I'm going to get 0. Okay? So, okay. So I now have the C plus and C minus. Let's put those on our table here also, because we'll need them. And I'll probably forget them in 15 minutes. So L plus 1 minus M plus 1. And C minus is H bar L plus 1 minus M minus 1. Okay, so we have all these. How are we doing on time? Okay. Let's see. Okay, maybe this is a good time to give a 4-minute early break, 10-minute break, and we'll see in 10 minutes.